Okay, I'm recording. I hope. Yeah, it's recording. Fine. So sorry about that. Next time, please remind me, okay? Sometimes I forget to record the class, all right? So kindly remind me because, yeah, I can be a bit loopy that way. So, what did I tell you? I said that, hey, listen, it's not a problem if you cannot just because the system is sitting in a superposition of these two states. I know that if the system was in psi a, I was very sure energy is going to be ea. If the system is in psi b, I'm very sure I know the energy is going to be eb. But now the system is sitting in a combination of these two, right? And superposition principle tells me that this is also a member of the ensemble. All right. So now the question is, what is going to be the energy when the system is in the state psi, right? And as I said, yes, you may not be able to say whether the energy is EA or EB, but you can definitely give what is called as the expectation value of the energy. So I'm going to now write down postulate 5 for you. Okay, so I'm going to go to the next page. Yeah, and I'm going to write down postulate 5 for you, and we will take it from there. All right. So what does postulate 5 say? Okay, so let me write it down first and then I will explain it to you completely. All right. So what it says is that if a series of measurements, so now we come to the idea that we cannot do a single measurement, but we have to do a series of measurements, okay, is made of a dynamical system, dynamical variable, sorry, A. All right. So this dynamical variable, I'm just kind of representing it by that fancy A. It can be position, it can be momentum, it can be energy. All right. Or it could be any other physical quantity that you can think of, length, weight, okay, anything. All right. All right. On an ensemble of systems which is described by the wave function psi, okay, then you can describe the something called as the expectation value. So the expectation value, now there is the expectation value is a very fancy term. You can also call it by a term that you are more used to. We can call it the average value, okay. So the expectation value or average value, okay, of this dynamic variable is, and what is it? Essentially you write it like this, okay. So please make a note of this symbol. All right, it's a less than and a greater than sign, okay. So it is this kind of a bracket, please remember it, okay, is equal to what? You basically can write it as psi a psi divided by psi psi. So what is this on top? Or you can write it as integral psi star a psi d tau divided by integral psi star psi d tau. Okay. Now you can do a few tricks over here. Okay. First of all, let's imagine that the psi is normalized. If it is normalized, then what will happen? If psi is normalized, what will happen? Essentially, you know that psi, the inner product is going to be equal to 1. Or we know that this integral psi star psi d tau will be equal to 1. Correct? Yeah, we know this. Now, uh, what do I want to say? So as a result, this denominator will go to 1, correct? So your expectation value of this dynamic variable will just become psi a psi. Okay, but this is only if psi is normalized, right? Now let's just spend 2 minutes trying to understand. Yes, Nayana, you have a question?
Yes, ma'am.
Yeah, please ask.
Ma'am, what do you mean by dynamic variable in this context, ma'am?
So anything that's changing with time, right? So for instance, you can have energy. Energy could be changing with time, correct? Yeah. So
Yes, ma'am.
any variable which is something which is uh, so for instance, position. Okay, so position can change with time. You know that energy can change with time. You know that momentum can change with time, correct?
Yes, ma'am.
There may be interrelations between them, but you know that these are all things which can change with time. All right. So we are
Yes, ma'am.
talking about such variables. All right.
Yes,
So such
yes, ma'am.
variables, they are associated with an operator, correct?
Mm. Yes,
And that
ma'am.
operator is supposed to help you get information about that variable, correct?
Mm.
Yeah. Go on. You have some more doubts.
Nothing, ma'am.
Sure, you
That's it.
understood this? Okay.
Yes, ma'am.
Yeah.
Thank you.
Any other doubts, please? Anybody else? Get it clarified now itself. Yeah. Don't hesitate. Yeah. I cannot even see your faces. It's all right. Okay. So now let us ask the question that I have kind of said this term series of measurements. Okay. So what do I actually mean? So what I mean is that uh, when you make a precise measurement, okay, all right, when you make a precise measurement, you will be measuring, okay, some value, and that there is no confusion in that value. Okay, so for instance, let us take this earlier case. Okay, as I said, you are trying to measure the energy, and the system is sitting actually in a combination of these two states. When you measure the energy, what will you measure? If you make just one measurement, you will either measure EA or EB. It will be a precise measurement. Okay? You will either measure EA or EB because those are the only, what did postulate 4 say? Those are the only precise measurements that you can make. But now, then, what is the confusion you can say? You know that for any physical system, you cannot measure just once, you should measure repeatedly. All right. So now let us imagine that you take the same physical system. Now, of course, you're going to be preparing it in the same way. Okay. It's the same physical system such that it is in the same state CA psi A plus CB psi B. Now you measure the energy again. When you measure the energy, you may end up getting EB. All right. You measure again. Maybe you get EB again. You measure another time. You may be getting EB again. Like this, if you make an infinite number of measurements, you will get a probability distribution of whether you get EA or you get EB. What determines that probability? That probability determination is from these numbers which are multiplying psi A and psi B. So this CA and CB tells you the weight with which the system is in psi A or it is in psi B. So please remember, precise measurements will only give you eigenvalues. But the system may be in a mixed state, and you will know how the mix that state is or what are these precise values of CA and CB only when you make a series of measurements. Okay, so you have heard, you see it in postulate 5. Let me just get back over there. Yeah, it is a series of measurements are being made of a dynamical variable, and then you can have an expectation value. So this expectation value, please remember, will roll in those weight fractions. Okay, so that C1 and C2, I'm calling them as weight fractions. Okay, so it will roll in those weight fractions, and it will tell you how many times you will be getting this EA measurement, how many times you will be measuring energy EB if you make an infinite number of measurements. And that value, that final value of the energy. So now let's imagine, okay, you're trying to measure the energy of an electron. And it can be either 1 electron volt Okay, so let us imagine you're trying to measure the energy of an electron. It can be either 1 electron volt or it can be 3.5 electron volts. Okay, and the system is in such a way that out of zero point 0.9 is the probability of measuring 1 electron volt, and 3.5 is the, you will get a probability of 0.1. Okay, all right. So now the question is, what is the expectation value of the energy? So if you did this calculation, which I have shown over here, what will you get as the expectation value? You will get zero point 0.9 into 1 plus zero point 0.1 into 3.5. This is the energy that you are going to get. This is the expectation value of the energy. Okay, because 9, if you measure 10 times, 9 times out of those 10 you will measure an energy of 1 electron volt, and only one time out of those 10 measurements you will measure 3.5. 10 of course is too less, so you can imagine, say you are measuring 1000 times, you're measuring 10,000 times. If you are measuring 10,000 times, 9,000 times you're going to measure energy of 1 electron volt, and only 1000 times you're going to measure an energy of 3.5 electron volts, and then you can calculate what is your expectation value of the energy. All right, is this clear to everybody what this expectation value is talking about? Has everybody understood? Any
Yes,
doubts?
ma'am.
Okay. All right. So, thereby, please remember, just because the system is not in a pure state doesn't mean that you cannot give an expectation value, an average value of that dynamic variable. You can actually do it, and that is what you do with these expectation values, which are defined in this particular way. And remember, if the wave function is already normalized, then the denominators will all go to 1, so you can completely ignore the denominator. A note of caution here, very often when somebody gives you a problem to find out the expectation value when the system is in some combination of these eigenfunctions of some Hermitian operator, make sure it is normalized. Okay, don't just rush into giving the answer, because very often they do not normalize it, in which case the denominator will not be 1, and you will get an answer, it look very correct, but actually because the denominator is not 1 and you've forgotten to do the denominator, you will get it wrong. Okay, so it's a note of caution to everybody. Okay, so now let's move on. So we have kind of tapped on what do you call it, on the expectation value. And now let's return once again to what I was telling you about this orthonormal set. Okay, and being able to express any state of the system as a linear combination of this orthonormal set. And I gave you an example. Excuse me, I need some water. Yeah, so I gave you an example of three-dimensional space, right? And I told you how basically any point in three-dimensional space can be written as a linear combination of these three unit vectors I, j, and k. Now I can ask the question is that, suppose now I have a position r, okay, which is written as some 2, 3, and 95. Okay, let's imagine I can write it like that. Now, that particular position in three-dimensional space, is this the only way I can write it? Or can I write it differently? Okay. If I can write it differently, then there's nothing so great about this system. Okay. So it is very important, firstly, that we understand that this linear combination is a unique one. So what do I mean by this linear combination is a unique one? Suppose now there are a set of eigenfunctions psi I of an Hermitian operator A. Okay, and I can write a linear, say, and there is a general wave function psi, which is equal to C1 psi 1 plus C2 psi 2 plus dot 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 some Cn psi n. So the question I'm asking is that, is this set C1, C2, Cn unique? What do I mean by unique? Is there only one way I can write it? So for instance, you know that this 2395 that I have written over here, okay? This 2395, this is a position in three-dimensional space, right? I know I can only write it as 2395. So now, when I give this set of numbers, 2, 3, and 95, you, me, somebody who is sitting in North Africa, somebody who is sitting in Brazil, okay, somebody who is sitting in Iceland, somebody who is sitting in Antarctica, we will go to that same position, correct? We will all know what this 2395 is, and your 2395, my 2395, the 2395 of that person sitting in Brazil is going to be exactly the same. What does it mean? That it is unique. That position is uniquely defined by this 2395. The question I'm asking is that, is this going to be also true when I write a wave function as a linear combination of these eigenfunctions of this Hermitian operator? Okay. Is that also going to be a unique set of numbers? Okay. So I'm asking whether this C1, C2, Cn is going to be unique. How do we prove this? We do it the typical way, which is that we assume that it is not unique and then go ahead and prove it. Okay. So let's try that. I'm going to go to another page. Okay. So let us write this down. Okay. The expansion of,
Ma'am, next page.
oh sorry, my apologies. Yeah, I kind of overwrote. Yeah, it just shows that I'm not used to this expansion. See, I changed a page here. Okay, I'm actually writing on paper, so I changed the paper here and somehow assumed that's how it is going to be on the screen that I'm sharing with you. So it's just, I'm working with some preset notions, classical mechanics. Okay. That's how my head is working. But I'm trying to teach you quantum mechanics. So I better learn to think more digitally, I think. Yeah. So can you all see this expansion of, okay? Expansion of a wave function in terms of eigenfunctions of a Hermitian operator. Okay. Yeah, so this is what we are going to essentially try and look at. And the question that we are asking is this going to be unique? Okay. So the first thing I'll try and prove to you is that the expansion is unique. So just give me, it's a very small proof. I will prove this for you and we will stop. Okay. I know it's a afternoon class. You've already sat with me for nearly an hour. I will finish it off fast. So what we do is that, so let us imagine that you have a Hermitian operator A. It has a set of eigenfunctions. I'm calling them Ui. Okay. Yeah, it is a. Now, what do we know? That since it's an eigenfunction. Yes, Nayana, do you have any questions? I see the hand raised again. Or is it from earlier?
It's earlier, ma'am.
Okay, fine, not a problem. Okay, so what do we know about the eigenfunctions of A? We know that if I take the the inner product of ui uj, it will be delta ij. So I hope I don't have to repeat it again, but I will say it anyway. Delta ij is going to be equal to 0 when I is not equal to j. It's going to be equal to 1 when I is equal to j. Correct? Now you have this particular situation, and I am saying that you can write one particular wave function as a linear combination of these eigenfunctions. Now the question is this expansion unique. Okay. So I'm asking this question, right? Now let us just go ahead and say it's not unique. Okay. So let us assume it is not unique. It is not unique. So when I say it is not unique, when I say it is not unique, what do I have to essentially do? I have to say that, okay, I should be able to write it, expand it out in a different way, right? So I can also write this psi as equal to summation over I di psi ui, sorry, di ui, okay? And what is important? That the di must not be equal to ci. At least one DICI should be different, correct? Okay, so we have to, if it is unique, then this particular thing, this DI not equal to CI has to follow. Now what do? We subtract. Okay, so this is now, let us say, equation 1. This is your equation 2. Okay, so subtract 2 from 1. Okay, so what will we get? We will get psi minus psi is going to be summation over I ci ui minus summation over I di ui. Correct? So what is our LHS? LHS is 0. Psi minus anything you subtract from itself, it will become 0, right? So it will give you a null, right? So this is giving you a null. And on the right hand side, what am I going to get? I'm going to get, so I'm going to put it together and I'll get Ci minus Di is equal to Ui. All right. Now what do? Let me take inner product with some uj belonging to this set of ui's. Okay, so I'm picking up one member of this set of eigenfunctions. One member. I'm calling it uj. Okay, so there's a whole set, like let's u1, u2, u3, u4, u5. Like that, I pick out u3. So one particular member I'm picking up. All right, and I'm going to take the inner product of this. If I take an inner product on the left hand side over here, I'm going to still get a 0, right? I try any inner product with a null vector, I'm going to get 0 only, right? There's no choice. So therefore, I will get 0 is equal to, let us now take inner product uj, comma, on this side I will have ci minus di ui. Okay, I'm taking this inner product. Now what will this be? That summation can actually come out, okay? Because inner product is only between those two eigenfunctions. So I can write it as summation over I ci minus di. Sorry, here I forgot to write the I. That is not good. Okay, I wrote it back again. Ci minus di, and then I will have the inner product uj ui. So what is the inner product between uj and ui? We know it forms an orthonormal set, right? So what will we get? We'll get summation over I ci minus di, and I will get delta ji. What is delta ji? It is going to be equal to 0 when I is not equal to j. It is going to be equal to 1 when I is equal to j. So when I is not equal to j, everything is going to become 0. So the only surviving member of this summation, we are summing up over here, right, is going to be cj minus dj into 1. For everything else, it is going to be, the delta ij is going to be, delta ji is going to be 0, correct? So now what do I get? I'm going to invert this and write. I will get cj minus dj is equal to 0, which implies that cj is equal to dj, right? So I've proved that cj is equal to dj. Now let us go and pick up one more ui. Okay, one more particular. So what did I say? I have U1, U2, U3, U4, U5, U6 like that. I picked up U3 and I proved that C3 is equal to D3. Now let's pick up U2. What will I, if I do the same procedure, what will I end up getting? That C2 is equal to D2. Like this, I can do it for each and every UI, and I will end up proving that CI is equal to DI. But this contradicts this particular statement, right? Where did I write it? That the DI is not equal to CI. So there is no way I can write down another linear combination like this where the DIs are not equal to CIs. So thereby the linear expansion is unique. Okay. So this is very, very important. The answer is okay. So have you understood this? Any doubts about this proof? Okay. So we can do this. We can repeat.
Ma'am,
Yeah.
is it the ji the term can become zero also, because we don't know whether the I and they are equal or not.
Just 1 second. Who's asking? Nana, isn't it?
Yes, ma'am. Yes,
Somebody
ma'am.
is unmuted. Please mute yourselves. Other than Nana, I can't hear what she's saying. Yeah, go on, Nana. Tell me, please.
We took ji term as one, no, ma'am. So
Yeah.
is we know that I j term are equal, or is it we are considering
See,
orthonormal?
yeah.
That
See, the
way.
point is, you agree with this relation, right? We know
Yes.
that this, look at over here, the inner product.
Yeah.
The inner product of ui uj is delta ij, correct?
Yeah. Yes,
So
ma'am.
now I'm getting a inner product here, right? Between
Yeah.
uj and ui. So that will
Mm-hmm.
be a delta ji, correct?
Yes, ma'am. Yes, ma'am.
Now this delta ji, now let us imagine the j was 3. I can
Okay.
go from 1 to 54, let us imagine. Okay.
Mm-hmm.
So when I is 1, what will happen? J is 3, I is 1. So this will be 0. Correct? Then let's say I goes to 2. Then j is 3 over here. We started off imagining j is 3, right? So j is 3. This is I is going to be 2. That is also going to be 0. Then I goes to 3, right? So here j is 3, I is 3. Only there it will become 1. So what will we get over here? The ci will be I is 3, right? So we'll get c3 minus d3. We'll get c3 minus d3 into 1 is equal to 0. Now let
Okay.
us imagine I goes to 4. So
4.
we'll get C4 minus D4. But over here, it will be delta of 3 and 4. That will be also 0, right? So the only term that will survive is Cj minus Dj. Is this clear? So like
Yes,
that,
ma'am.
I can pick up different uj, all right? And I can prove it for all of them. I can slowly prove that C1 is equal to D1, C2 is equal to D2, C3 is equal to D3, C54 is equal to D54. So thereby, it is not a unique, it is not a different expansion at all, this one. It's the same expansion. So thereby, I have to say that there is only one way in which I can write this wave function as a linear combination of all those other wave functions. Is this clear?
Yes, ma'am.
Anybody, any other doubts? Fine. So what we will stop here, but what I will like you to understand is that you may still think, okay, it's the expansion is unique, so what's so great about it? Okay. The answer is here. You remember I said that this position 2, 3, 95. What are they actually? 2 is the coefficient of the I vector, that unit vector I, right? 3 is the coefficient of the unit vector J. 95 is the coefficient of the unit vector K. So here by just writing 2, 3, 95, okay, we are able to uniquely define something, correct? Now the point is, if we have a unique expansion, all right, just by knowing these CIs, we will know this particular wave function. Okay, so that's the idea. The idea is that we'll forget about all these complicated wave functions, these mathematical, these will be all nasty mathematical functions, these UIs. We don't want to write them all the time. All I want to do is write down these numbers, these CIs, C1, C2, C3, C4, C5, C6. Okay. And I will immediately know what the wave function is. So that's a very nice, neat method of writing the whole thing. Okay. So that's the basic idea. That's what we are going to try and do. Okay, I'll kind of revisit this on Monday, all right, when I have my other class, all right. Because yeah, Meera ma'am and I did an exchange of classes, so I will be handling one class on Monday. So yeah, so we will see each other on Monday, and I hope if you have any doubts, I can still wait. Please ask. Otherwise, yeah, we please read up, and then you will have your doubts ready when we meet on Monday. Is that okay? You're all
Yes, ma'am.
asleep. Okay. So I will stop my sharing. Oh, how do I stop share? Oh, there it is. I will stop my sharing. I'll also stop my recording.